In part 7 of section 16, we're going to be putting all the other parts together, and we're going to be looking at how to graph a rational function. So I have a procedure here for us that's going to walk us through all the steps that are necessary to come up with an accurate graph for a rational function. First step is to determine the largest possible domain. The largest possible domain is going to tell you if you have any domain restrictions. Those domain restrictions are going to lead you directly to the discontinuities of this function. Your discontinuities are either going to be a vertical asymptote or you're going to end up having a hole. Now you could have both. If you have multiple discontinuities, you could have one that's a vertical asymptote and one that's a hole. But these are the things that you're looking for here with your discontinuities. Now while we're on the topic of vertical asymptote, the third thing I look for is a horizontal or slant asymptote. It is not possible to have both. You will either have one horizontal asymptote or you will have one slant asymptote. You will not have multiple of those, just one or the other, and that's it. Step number 4 is then going to recycle the ideas of x-intercept and y-intercept from polynomials, and really any other function that we've ever dealt with, we could always do that particular calculation. So this is going to be both x-intercepts, which could have more than one, and it's also going to include the y-intercept, if there is one for that. And then I have a step 5 here where it says to complete a t-chart, and we'll talk more about that when we look at the first example. And then finally, once you're done with your step 5, you make your sketch. You'll put everything together. So let me go to the next slide, and we have an example already waiting for us here. It is example 16.12. It says let f of x equal 3x divided by x minus 1 be the equation of a rational function, and then it just says sketch the graph of f. So it's going to be difficult to sketch the graph of f without going through that procedure that I prescribed. So let's first start with statement of the domain. The domain of this function is going to have one restriction. It has a restriction of positive 1. So that positive 1 needs to be tested with the equation. So I'm going to test out f of 1. 3 times 1 over 1 minus 1. It's going to give me 3 over 0. So that is undefined, not indeterminate, it's undefined. So since that is undefined, this would imply that I have a vertical asymptote located at x equals 1. Now as far as the holes are concerned, I can tell you that there's not going to be any holes because I only had one discontinuity, and we just showed that that one discontinuity was a vertical asymptote. Moving on to step 3. Step number 3 is where we look at the horizontal or slant asymptote. This particular rational function is balanced. When it is balanced, I am expected to look at the leading coefficient from the top, leading coefficient from the bottom. That's going to be just 1, so 3 and 1, and that's going to reduce to just 3. So my horizontal asymptote is the equation y equals 3. So if there's a horizontal asymptote, there cannot be a slant asymptote. So we're done with step number 3. Step number 4 is to find the intercepts. For the x-intercept, we're going to let f of x be equal to 0. And then that's going to give us the following statement. 0 equals 3x times x minus 1. I will then multiply both sides by x minus 1, so that way on the right side it'll cancel out with the x minus 1 that's in the denominator, but on the left side I'm going to be multiplying x minus 1 by 0, which is just going to still be 0. So it really reduces the amount of equation that I have to work with. It just tells me that 0 equals 3x, which would then imply that x has to be equal to 0. So there is a x-intercept located at the origin, 0, 0. The y-intercept calculation is going to be done by looking at f of 0. F of 0 will be 3 times 0 over 0 minus 1, which will be 0 over negative 1, which gives us 0. So that implies that the origin should also represent the y-intercept. So let's go ahead and take the information that we have, put it onto the graph, and then from there we can look at the fifth step where we're supposed to be making a t-chart to help us before we sketch. So we have one ordered pair with 0, 0. We have a vertical asymptote at x equals 1. And we have a horizontal asymptote at y equals 3. This is really all the information that we have. So the table is going to help us to be able to come up with a few extra points, so that way we can really see what the curve is going to look like, but the asymptotes are going to help us to stay within the boundaries and also give us the correct end behavior. So one thing I want to point out now is that the domain is written in two intervals, negative infinity to 1 and then 1 to infinity. Everything from here up to the vertical asymptote, that is going to be your negative infinity to 1 interval. So there's going to be one curve drawn to the left of the vertical asymptote. And then there's going to be the same idea happening here to the right. That's going to be the 1 to infinity interval. So there's going to be two curves here, and then both of these curves put together are going to represent the graph of f. So I'm going to make two t-charts. I'm going to make one t-chart for the first curve. I'll call this x, f of x. And I'll do the exact same thing for the second piece, x, f of x. And you just have to start picking x values that you think are going to be of interest and calculate the corresponding y value. So that's just going to be a matter of plugging them in and calculating them. So I've already done some of these calculations, so that way we don't have to go through and plug them all in here. I can just get you to the point where you have enough ordered pair on the graph, and then we can connect the dots. So for example, with this first part, I have the origin already known, but it would be nice to know something that maybe is a little bit further to the left. Say, for example, what's happening at x equals negative 5. So when x equals negative 5, after you plug negative 5 back into the original equation, you're going to end up with 5 over 2, which would be the same as saying 2 and 1/2. So let me come over here to negative 5, and let me mark a point at 2.5. And then it might be helpful to get a third point, so that way you can actually see how it curves, because with only 2 points, you might be tempted to try to draw a straight line, and these are definitely supposed to be curved, so that way you can stay within the boundaries. So let's go to, say, negative 3. So if we go to negative 3, then I've already done that calculation as well. The y value will be 9/4. That is equivalent to 2 and 1/4. So at negative 3, I'm going to go to 2 and 1/4. And so we can start to see how there is some curvature here. And I want to be able to connect all these things together. And now I'm on the, in the fourth quadrant, I'm underneath the x-axis now. And so from here, I'm just going to continue on down and get closer and closer to that vertical asymptote. And then to the left, I'm just going to continue to get closer and closer to the horizontal asymptote as I go to the left, and this is going to give me what the curve should look like from negative infinity to 1. If you want to add more points, you are more than welcome to add more points, but I think 3 would be the minimum we need here to be able to get that accomplished. So now let's look at the second interval from 1 to infinity. This one we don't have any points, but we do have the boundaries from the horizontal asymptote and vertical asymptote. So for this one, I'm going to look at probably using 2 for an x value, and then also 5 for an x value to start. We can add some more if we need. 2 is going to map to 6, and 5 is going to map to 15/4, which is equivalent to 3 3/4. So let me mark a point at 2, 6, another point at 5 with 3 3/4. And again, with only 2 points, it's very tempting to just draw a straight line when there's supposed to be more of a curvature to it. So it probably is best to go ahead and get another point on here. So I'm going to go ahead and look at 4, and 4 is going to map to 4, so I'll have another point here at 4, 4. And if you wanted to pick different points, that's perfectly fine, but the only way I'm going to be able to connect all 3 of these points together is with a curve, make it smooth and continuous for this one piece, and then you stay within your boundaries, and all of this together represents the graph of f.